Hello everyone. Today this brings me to my fourth presentation, my fourth video in the series on my conference papers. This conference paper again takes us back to the ARRB conference in 2014, and the title of this paper is Calculation of Transport Mode Shift in the Absence of Complex Transport Models. So what are we going to do if we don't have a sophisticated transport model? So what I'm proposing in today's video, in this paper, is to develop a rapid model. So why wouldn't we be able to get hold of a fairly complex, sophisticated transport model? Well, for starters, any transport modeling, any sophisticated transport modeling costs quite a bit of money. And often the projects don't have sufficient budget to actually pay for these models or pay for the consultants to actually run these models. And secondly, there's often a time constraint as well. Many projects actually have very, very tight deadlines. In order to meet those deadlines, the modeling has to be done reasonably quickly to allow enough time for other things. For example, the economic modeling that would often follow afterwards. And if we don't have the time to do that, a better solution than to not do any modeling whatsoever will be to conduct a rapid analysis using a rapid transport model. What I'm now going to do is introduce you to what I call the TRI methodology. So TRI as in for triangle, and of triangle distribution. So this is a triangle distribution of users' perceived costs for various transport types. So for example, you can see the three triangles. So one triangle would be for buses, one triangle would be for cars, and one triangle would be for trains. And this is the distribution of people's perceived costs. So some people will have higher perceived costs than other people, but the use of the triangle then still gives us that central tendency that you get with a normal distribution. But it's a lot easier to calculate than using a normal distribution, and there's a lot more flexibility as well using maximum, minimum, and mean. So what I'd like to introduce you to now are perceived costs. So here we have what we call perceived cost functions. So I've got two functions here, one for public transport and one for private cars. So let's first take a look at the public transport perceived cost function. So people on public transport perceive that there's a cost for fares. So basically that is what you're paying, your ticket price, or use your card to get onto the train or onto the bus to get you from point A to point B. There's also a perceived cost for time as well. And that time will vary depending on what you're doing. So people have a different value for time on a train compared to waiting at a station, compared to getting stuck in delays. There could be a traffic jam if you're on the bus, or the train might be late. There will be, again, a different perceived cost for transfers, going from one station to another station to catch a different train. Whereas for taking a private car, again, we also have a perceived cost function, but it'll look a little bit different. So for example, we wouldn't have fares, but we may have tolls. You may need a toll in order to get somewhere, whether that be a toll going across a bridge or a toll for using a motorway. And when you reach a destination, you may in fact have to pay for parking. So again, these numbers are usually fairly obvious and people have a very good idea of what they are. But it gets a bit more subjective when we talk about value of time again. And people value time differently to whether they're actually driving their car, or whether they're stuck in traffic jams, or there's some other unexpected delays. So again, that's very similar to what we have with public transport. So these perceived cost functions actually feed into our distributions. So we'd use a median value for all of these, as well as a maximum and a minimum. And that would shape our triangle that I mentioned on the previous slide. There are a number of different distributions that we could have used. Like I mentioned earlier, we went with the triangle distribution because it's fairly easy in a sense. It's also fairly flexible as well. In a sense, you have a maximum and a minimum. There are a number of other distributions that are worth considering too. Like for example, there's the normal distribution, which again, you got your central tendency, but that is quite difficult to calculate. And also you don't have a maximum and minimum in the sense that they go on there continuously. So you would have various standard deviations. So you probably work between two standard deviation either side of your median value. There's also a PERT function, which is actually quite good as well. You can have a maximum and a minimum on that. And there's certain flexibilities around parameters on that. Again, we went with the triangle version because it is easier to calculate. And this is a rapid model. And triangle generally gets us what we want, what we're looking for in terms of a distribution. And it's also, we found it easier as well for calculating. in terms of the interactions between the triangle and also determining mode shift when these triangles shift when there are changes in costs. And these costs could come about because there's an upgrade, or it could come about because there's been a deterioration in the road conditions, for example, so there's more delays. So that cost function is actually becoming larger. So people are actually got higher costs of traveling by car. Or again, same thing with trains as well. You could be putting more trains on, so less waiting time, or trains could become more crowded. So in fact, there's more discomfort of riding. So all of those would cause your distributions to shift. So now we're going to take a look at our triangle distribution and how perceived costs are actually applied to that. So you can see here in the figure, so we've got on our y-axis number of road users, and on our x-axis the perceived costs. And we've got two distributions here, one for private cars and one for buses. So the black line, that represents private cars. That's the distribution perceived costs of traveling in private cars. You see the blue line, that's the distribution of perceived costs of traveling in buses. So as we got here, we've also got tolls, parking, and bus fares. So we've made the assumption that everybody who's traveling by car perceives the tolls and parking fees to be the same. So if the toll is $2, everybody perceives $2 as $2. If parking is $5, everybody perceives parking $5. There's very little subjectivity around those actual figures because that's the amount they're paying, and we assume that's the same for all vehicle types. In regards to bus, we're assuming those are all getting on at the same bus stop and traveling to the same destination would have the same bus fare. And that would be, let's say it's $8, for example. And everybody perceives that bus fare the same. $8 is $8. And there's little subjectivity around it. For the rest of the distribution, mostly relies on travel time costs. And that, again, links to, like, for buses. People will add certain weightages to traveling on the bus, waiting for the bus, and all of that. And that potentially can vary quite considerably for different people. Some people aren't bothered by crowded buses. Some people aren't bothered waiting for the bus. So they don't really perceive that as a cost. So they'd be in that minimum area, whereas others just can't stand being on a bus. They don't like the crowded bus. They don't like people, getting in their area, getting in their comfort zone, or all that sort of thing. They don't like waiting for a bus. So they have a very, very high cost of actually waiting for a bus. So again, we look at cars. Again, some people don't worry too much about traveling in a car and the cost of traveling. Some people worry a lot more about it, and some people really don't like, for example, if there's traffic jams. That really, really frustrates them. So waiting in a traffic jam has a very, very high cost to them. So what we've got now, we've got these two distributions, and these two distributions interact with each other. So look at the first part of our car distribution. So that is the difference between bus fares, tolls, and parking. So all of those that fall within that area are always going to travel by car because their minimum cost of traveling by car is below the minimum perceived cost of traveling by bus. So we move further along. So now we've got this section between the minimum of traveling by bus and the maximum traveling by car. So we've got people in there that could go either way. Some may travel by bus, some may travel by car. So how that's calculated is the actual areas underneath between those two are the number of people that are actually traveling. So we've got quite a large section under cars and we've got a smaller section under buses. So if you actually calculated that, more people falling between that range are still going to travel by car. Then we've got the last segment. So that is maximum cost of traveling by car and the maximum cost of traveling by bus. So all of those people in that area would assumably all travel by car. So that is quite a significant proportion of your cost. So if you go to the paper, it's a little bit hard to explain just using diagrams. I've actually got the mathematical formulas explaining how the interactions are calculated, and it uses calculus in terms of calculating the areas underneath the two distributions and also the interaction between those. So if you see a shift in any of these perceived cost curves, it's going to give you a different number of people using buses or cars depending on what that shift is. So again, that actually goes into the formula. So for example, if the cost for buses were to decrease and you'd have, like fares for example, that'd be an easy one to explain. So if bus fares were reduced, went down from 8 to let's say 4, you'd see a shift of that whole bus perceived function, and then you would actually see a larger overlap with the cars, and you'd actually have people, should have people switching based on these distributions to using buses. What we also must bear in mind as well is that some costs are unperceived while other costs tend to be overperceived. So if we look at our costs are unperceived or underperceived, it'll be things like emissions from our cars, the externalities that they cause, the air pollution, the water pollution, and the noise pollution. We're often not aware of those costs when we're driving to somewhere in particular, but it's the people around us that are actually experiencing those costs, or all of us in the sense that we have some longer term costs of pollution being caused. Many of our vehicle operating costs as well for car users is actually unperceived. Well, at the time of journey anyway. They may be perceived once you're having your car repaired or changing your tires and stuff like that, but people don't necessarily factor in the tire wear when they're driving from one place to another, or the general wear and tear on the vehicle from driving from one place to another. What tends to be overperceived though is fuel costs. So the cost we pay at the pump, the price we pay at the pump, is not reflective of actual resource costs because of fuel tax. So again, that is something that could be most likely overperceived by people traveling. Another one that's often overperceived is actually public transport in general, the cost of public transport in terms of paying fares and how much time people have to wait and how much time they have to allow to get from one place to another. I'm now going to introduce you to the concept of consumer surplus. So what is consumer surplus? Consumer surplus is the difference between what someone's willing to pay and what someone actually pays. So take, for example, we've got an upgrade in public transport. So the upgrade should result in a reduction in cost. For example, you have more trains. So there could be less waiting time, or you may not miss a train because it's overcrowded, and stuff like that. So you would actually have a reduction in cost. So if we look at our demand and supply curve, so if we see a reduction in cost, our supply curve should move down, move to the right, and we'll have a lower in perceived cost for the individual, and that lowering of perceived cost is going to increase consumer surplus, and that increase in consumer surplus is actually going to encourage other users. So that's where we would get our mode shift. So, and also we could also have some induced travel as well out of it. So those additional people that are now using the public transport because of the upgrade, they could be shifting from cars, and they could also be coming from elsewhere. Maybe they weren't traveling at all. Now that the cost of using the train, they actually, maybe will travel a little bit further afield, for example. So instead of just going down to the local shops because the trains are too difficult or are considered too costly to actually go somewhere else, people now may actually take the train and possibly go to another area that they found more favorable than their local area, simply because the cost is lower. So let's now have a look at the change in consumer surplus for cars, for example. So if the train has been upgraded, we've got more trains on, so that's going to lower the cost. So therefore people are going to shift from car to train. So what does that look like? So that would be a shift in demand. So if you've got a shift in demand, that could be easing some of the congestion on the road, for example, if it's getting close to congestion. So that would lower the perceived cost of traveling by car. So what happens here, we actually will have some benefits to the car users, and also there will be a gain in consumer surplus to those staying on the road. So they also get a benefit as well from this mode shift. So when we look at transport, we don't actually have demand for transport itself, but the demand is for another activity, the activity that you want to get to. So the demand could be getting to work, the demand could be going to a shopping center, the demand could be going to the theater, or any of that stuff. We don't actually demand directly anyway the use of transport. So it's a derived demand based on the utility that we derive from other activities. So if we assume that traveling by bus or traveling by train or traveling by car are actual substitutes for each other in order to get us to where we want to get to. So in a sense, that demand is actually, it's the same demand function, you know what I mean? So in this case, we got in this diagram, we've assumed an inelastic, perfectly inelastic demand. So we're not actually assuming in this case, very simply, we don't have induced demand. So we're assuming, let's say for example, we have 5,000 people traveling by car and 2,000 people traveling by train. So for example, if there are now 3,000 people traveling by train we'll now have 4,000 people traveling by car. So you'd have a total of 7,000 people. So we're saying it's a fixed demand, but potentially the cost could change. So what happens here? So we see CA1 and CA2. So that is, let's say, an improvement in traveling by rail. So that cost has actually gone down. So that's a shift. So, and whereas our costs for traveling by road, we've assumed that to be constant in this case. So what happens to our overall costs for traveling to, let's say, the theatre? So as you can combine the supply curves together. So now we have E1 and now we have CA1 and CA2B. So there's an overall shift in the cost of actually reaching our destination. So that shift you can actually use to calculate the number of people that are going to switch from car to train by this upgrade. And it all really depends on the elasticities of these these cost curves, these perceived cost curves. So you can see here we've actually got an increase in the number of people using train. So we're going from X1 to now X2 people. And then the difference between X2 and DX, that would be the number of people using car. So as you can see here, we're assuming that we have this flexibility that it's not about the journey, but it's about deriving utility from the activity at the end of the journey that's stimulating this demand. Again, it may not be entirely true. Some people actually enjoy their cars, and maybe some people actually enjoy the train. But just for the sake of this rapid model, we've actually assumed that they are substitutes for each other. Actually, almost, I won't say perfect substitutes for each other, but substitutes in the sense that the overall goal is to reach your destination and not about traveling the journey. So now I'm going to show you how this methodology has been applied. So you got this model here is called TRIM. So this is the triangle multimodal model. So as we explained earlier, we've got these distributions of perceived costs for cars, buses and trains. So this model actually takes that into action, but it applies it to non-infrastructure initiatives. And what this model can actually do is it can actually, we've actually got sensitivity here to things such as improved quality of facilities, improved quality of information, changes to the number of buses or trains, inclusion of air conditioning, changes to tolls and fees, and changes to parking fees. So all of these things actually fit into the model, and all of these parameters shape the function, the distribution of perceived costs. So we have a median and we have a low and a maximum that shapes our perceived costs. So whenever any of these change, like for example, if there's an improvement in information, that will actually lower the cost, the perceived cost, because people can actually arrive when they want to arrive. So you don't have to spend too much time waiting for their bus or train to arrive. So that would lower the perceived cost of taking a bus. In a sense, it could actually cause a mode shift. Again, air conditioning was actually fairly sensitive. It gives you a far more comfortable journey by traveling in an air-conditioned bus or train compared to previously unair-conditioned buses where we're in a hot place like Queensland or Brisbane. You find that it can get very hot in the summer, and air conditioning is actually quite important and actually will attract more people to buses and trains, especially when people have air conditioning in their cars. Another one is the impact of frequency. So if you increase the frequency, again, that's going to reduce waiting times potentially. And also it could reduce your overcrowding as well. So all of these things have been factored into the TRIM model to determine the shape of these distributions. And then these distributions interact with each other in order to determine how many people are actually using the buses and trains and cars. And this is fed off of actual data. So data will be actually fed into the model. So that will give you your current usage. So how many people are currently using cars? How many people are currently using trains? And it will use that actual data to actually generate the perceived cost function. And what, again, it's not going to give you exactly the answer you have with the actual data, but actually uses the input data to create those functions. And you'd have a medium and you'd also have your maximum and high generated from those numbers. So here we have an example of how the TRIM model works. So in this case, we've got an example of increased bus frequency. So putting on extra buses. So what is the benefit of doing that? So we've broken down the benefits here by travel time costs, vehicle operating costs, accident costs, emission costs, and other externality costs. So why are we getting accident costs? If you're actually taking vehicles off the road because people are using buses now, you're going to have less accidents simply because you have more vehicles. Again, we've got emission cost savings, less vehicles. Again, you'll have less emissions. We've got some travel time cost savings and some vehicle operating cost savings. And travel times, again, coming from people, existing users. So you've got less wait times now because you've got higher frequency. So in a sense, you won't have to leave so early, I suppose, to get to the train station because you won't have a less waiting time. And also, as well, it's also factoring in if you have to be somewhere, let's say 9 o'clock, and the buses will get you there at, let's say, 8:40 or 10 past 9. You'll be required to get there by 8:40 because you can't be late. So you've got 40 minutes that are wasted of getting there early. If you've got a higher frequency, you might be able to get there at 10 to 9 now instead of 22. So you have that savings as well by the increased frequency if you have to be there at a particular time. It could be at work, for example, at that time. We've also got some additional information in regards to revenues as well. As we can see, actually get some additional revenue from buses, but there'll be lost revenue from parking because people are switching from car to train. So there'll be less money going into parking and more money going on to bus fares by the increased number of people. So the results of this analysis gives us a benefit cost ratio of 4.75 at 4%, or a net benefit investment ratio of 2.62. Net benefit investment ratio is lower because that is basically divided by capital. As you can see, the capital costs here are reasonably high, which we've got some savings in regards to operating costs of the trains compared to some of the older buses and trains and stuff like that. So in conclusion, I'd like to say that we have fairly successfully developed a rapid model of determining user behavior and user shifts in the absence of complex models, and that methodology has been applied to a model called TRIM, which is a triangle multimodal model, and that model has actually been used, and in the example of increased bus frequency, it's actually been used to determine the benefits of a project that actually involves increasing the bus frequency and using those triangle distributions. And what those triangle distributions are the perceived costs and their relationship with each other. So you'd have the three triangles, which would be your car, bus, and train. In the case of bus, we didn't include train, but the interaction between those distributions determines the mode shift. So if there's a decrease in the cost of traveling by bus, so you would see a shift in that distribution, and you'd see a smaller overlap, or we might see a lot, depending on where they're placed. And that change in overlap reflects the number of people switching from road to bus because of the upgrade. And this video is actually demonstrated on how that can be done and how that can actually be applied to a model. So I'd like to thank you for listening in on another one of my videos of one of my papers. I'll have more papers and videos to come soon regarding conferences, and some more papers as well. Some more videos as well relating to some other topics relating to economics. Thank you.
If you like today's video presentation, just click the like button and the subscribe button, and I'll be uploading several more videos in the weeks to come. Again, within the same series, videos relating to the transport conferences, as well as several other videos also relating to economics. If you want to find out more about today's paper, just go to my website at spectrumecons.com and you go to the research paper, just click the link there and you'll get the paper in full. Again, thank you for listening. Goodbye.